good morning for everybody. Well, I will talk you, I think, about 30 minutes about these definitions. I was chairing the task force in the REHVA to prepare this uniformed definition, and now actually we are in the revision process as it was prepared already last year. And then I will talk you about a couple of case studies of office buildings which are maybe more focused on technical solutions for nearly zero energy buildings. So the correct term we are speaking because of the directive is nearly zero building, not net. Directive doesn't know the term of net. Indeed, net is very much used in scientific communication. So nearly zero energy buildings might be seen as some sort of systemic change in the construction sector, and many countries already have prepared roadmaps with very detailed targets for this kind of buildings. In some countries this is because of requirements of a directive, but in some countries because of longer tradition of energy performance improvements. For example, Denmark is a very good example with very long track on this field. And indeed, it's good to define numeric targets in order to take this possible for the industry to be committed and to be prepared, because we are speaking still about something that is quite a long-term target, speaking from 2021 and so on. Well, you may ask what's the purpose of these nearly zero energy buildings. It might look too complicated to construct such buildings, but we have very well defined goals in the Europe 2020 growth strategy, where this belongs to one target of 5 targets. So energy and climate change is one target. We all know these 2020 targets, and these nearly zero energy buildings really contribute to new buildings, new construction, and then the aim is indeed to reduce energy use in the building, and as every reduction has some limit, then you need to compensate the energy use in the building by on-site or nearby renewable energy production from renewable energy sources. So these are also the terms from the directive, but basically we mean distributed generation or thermal energy production by these ones. And this example shows the situation in Germany. They have already installed a lot of photovoltaic, so solar electricity production, and when you compare these distributed generation to centralized production of electricity, then you can see in the profile of a final energy, electrical energy use, that if you install some defined amount of PV, then you are able to cut the peaks. If you will install much more, then you will produce new peaks. But if this is done in proper fashion, then you can say that distributed on-site production can support centralized production, so that you have less peaks. This example applies for the summer days, and you can see a lot of daily fluctuation. That's typical for all countries, because we sleep at the night time, and in the morning and the daytime consumption is much higher. Well, this is some very short introduction to the topic. My presentation will focus, I will tell you a few words about the directive, and then we'll focus on these definitions and go through some case studies of office buildings where I have tried to identify key technical solutions needed for such high-level energy performance and try to show what solutions have been common solutions used in such buildings. Well, this directive, energy performance of buildings directive, called EPBD, recast because the original one was given already 2002 and the recast 2010. So it includes the requirement of cost optimal minimum energy performance requirement. So it means that in every member state you need to check your requirements, are they on cost optimal level or not. And this basically we speak about when we speak about energy performance requirements, when the directive requires to use primary energy indicator for these, and it has to be a primary energy leading to minimum life cycle cost in the buildings. But I will tell a few words more about this cost optimality procedure because there is special European regulation how to conduct these national cost optimality calculations. And when we have this target for the nearly zero energy buildings, this is from 2019 for public buildings public authorities will occupy, indeed for new buildings, and from 2021 for all new buildings. And already a lot has to be done in every country because the laws and regulations shall already adopted was last summer, and most of the requirements shall apply from January next year, but indeed not these requirements. But basically the intention is that in every country these nearly zero energy building requirements will be defined. Indeed they are not mandatory right now, but will be in the future. So this cost optimality can be seen as a first step towards nZEB buildings, and all the member states have to produce such cost optimality calculations, which are basically a life cycle investment calculation with net present value method, where you calculate life cycle cost, what will form from the investment cost, so meaning the construction cost, plus 30 years discounted energy cost and maintenance cost for residential buildings. In non-residential buildings the time period is 20 years. So it's a simple investment calculation, and you should prove that national minimum requirements lead to minimum life cycle cost, and this is called by this regulation cost optimal energy performance level. So this is done only for the national requirements, not in every construction project in the design. No need to conduct these calculations. Indeed, if a client wants to have some investment calculations about the energy use life cycle cost, then that's a different matter, but this is required once for every member state, and then to report to Brussels. And if national requirements are not on cost optimal level, then you need to report measures that you intend to implement in your country to move to cost optimal level. And there is a procedure for that. So that's very strict requirement. There is still some time left to March next year, because this regulation, cost optimal regulation, was published in March this year, and when you have 12 months science to report national cost optimal calculation. For example, in Estonia, these are already completed, these calculations, and we are moving from next year to new revised primary energy requirements which are based on cost optimality calculations. For example, in Finland, these calculations are still ongoing. I don't know what's the situation in Latvia, but most likely that's the same question for you. Well, when just a general definition of energy performance in the directive, it's not exactly the full definition, because if you measure energy use in the building when you have electricity, gas, oil, district heat, might have district cooling, energy bills, and complete energy use in the building. But in the directive it is defined so that you may left out these other services. So energy performance of a building should include energy used for heating, cooling, ventilation, hot water and lighting, and these energy use means also electrical energy for HVAC systems. This is included, but these other services, so all the computers and household equipment in homes, these may be included or may not be included. So in some national definitions only these are taken into account, and in some national definitions all energy flows are taken into account. And it is indeed a bit confusing, because in order to prepare energy calculation you need also to know what are all the internal heat gains. You need to know all electrical appliances installed in the building. Well, now I'm moving to this REHVA definition, and when the history is so that when this directive was launched, 2010, when based on the directive every member state needs to define what these nearly zero energy building requirements exactly mean in the specific country. And to do that, you need a definition for nearly zero energy building, how it will be calculated, what will be the system boundary. All these technical questions needed to be solved before you can set requirements. And in REHVA, we really realized that there will be a problem in Europe, because general principles and guidance in the directive could lead to very many different definitions all over Europe. For that reason, we established a task force in order to propose a uniform common definition for nZEB, and when we did that in 2011, at that time we had only published 10 EPBD standards, so the European standards, what did not include any word about nearly zero energy buildings, because they were published before the recast of the directive was given. Currently these standards are also under revision, but this will be a longer process. It will take at least 3 years to revise these 42 European standards on energy buildings, and indeed one standard is the major standard with these definitions, but the existing ones were not possible to utilize completely because not included nearly zero energy buildings, and also having some national options regarding system boundaries, so what energy flows are taken into account or not, and there was a possible conflict depending on national choices regarding these renewable energy sources. So in this situation in REHVA we prepared a uniform definition what was launched in May last year, and actually this has been the only methodology available in the level of detail that you can implement into the building codes and the regulation. And this indeed has been the reason this methodology is quite a lot utilized in many member states, and it has been also very popular. This year, in April, we decided to start a revision, and when it was viewed and downloaded very many times already. So what are major issues in these nearly zero energy buildings? So basically we are interested how much energy will be delivered to the building and how to reduce the amount of that delivered energy. So it means electricity, district heat, fuels, district cooling. And to do that, you have basically two possible options. All the demand reduction measures and effective technical systems to reduce energy use, but indeed this reduction has some limit, and after that you need to start to compensate, what means you need on-site production from renewable energy sources, for example thermal, solar electrical, GHP, sometimes wind can be used and so on. And this on-site production can be directly reduced from the delivered energy if it will be fully utilized in the building. But in the case where you have, for example, you have a lot of solar production in the summer and you don't have a load in the building, in such a case you need to export this energy to the grid. So the basic energy balance is shown here for both for the thermal and electrical energy. It applies that delivered minus exported energy, it equals energy use in the building minus these on-site renewable energies. So it's the balance shown by this system boundary line, which can be interpreted as a building site. So it's a physically building site is defined by the directive as the system boundary. And these can be seen as connection points to energy networks, to electricity grid, district heating, or when you deliver the fuel to the building in the same way, and you should be able to export energy. That's very obvious. For example, in office buildings in July or August you can have holidays, buildings is almost closed, but you have a maximum amount of solar electricity production, and indeed in such a case you need to export these to grid. And this primary energy indicator, what is required by the directive as a measure of energy performance, this is calculated very easily if you know delivered and exported energy flows. It's just delivered minus exported energy multiplied by energy carrier factors, so by primary energy factors, and calculated separately for each energy carrier when summed and divided by net floor area, which definition you should have a national definition. In some countries it is heated area, in some countries it is just net area, in some countries it is conditioned space, and so on. But that's the basic definition, and in older version we have the slightly more simplified format, so that the primary energy factors were equal for delivered and exported energy. But in the new version we have recognized that you may use one primary energy factor for delivered electricity and somewhat different primary energy factor for exported energy. So these can be equal or cannot be, depending on national choices. And basically the directive says about nearly zero energy buildings that such buildings have to have a very high energy performance, and significant amount of energy should be come from renewable energy sources, included production on-site or nearby. So basically, by the definition of the directive, we have two components, very high energy performance plus on-site renewables, but every member state needs to define what it will mean. A very high it will mean in Latvia, in Estonia, so on, and what the significant extent will mean. So no numbers are provided in the directive, and this depends on the national definitions and national ambition level, so on. When we prepared this definition, original definition last year, one of the most difficult questions because of these European standards, what's the major standard of energy performance science now from 2008, and how to take into account this on-site renewable energy production. Can this directly subtracted from delivered energy or not? This was one of the major discussion, and in REHVA we decided that all possible measures should be equal. So the measures related to thermal insulation, to technical building systems, or on-site energy production, all measures should be treated in equal way. So it means that everything should be inside the system boundary, and then cost effectiveness should show which solutions are appropriate for each project. And actually this basic principle was confirmed by this cost optimal regulation, where it is said that these RES-based active technologies should enter into the direct competition with the demand-side solutions, so that cost optimality should identify the best solutions for every building. And this has been a very strict debate in European level. Should we distinct between demand-side reduction measures and renewable energy measures or not? Now the answer is we should not, because it is not easy to give any consistent definition how to distinct that first insulate the building envelope to a certain extent, and then continue with HVAC systems, and then continue with on-site renewable energy solutions. This is nice principle for the design, but you cannot put it into the definitions and to give numeric values for the limits, how much you need to insulate, how good HVAC systems you need, and how much you will need renewable energy production. This is not possible in the definition level, and that has been the reason that all possible measures are treated in equal way, and cost optimality should show which are the best solutions. And another discussion has been on the primary energy factors, but this is not so strict discussion, because every country needs to define primary energy factors, and basically they should be non-renewable primary energy factors in order to be able to take into account renewable fuels, positive effect of renewable fuels. If you will use total primary energy factors, when for example biofuels have a factor 1 which is equal to fossil fuel factor similarly 1, and no difference in the energy calculation and in the primary energy indicator. So that's the reason you basically need to use non-renewable primary energy factors, and this is also required by this cost optimal regulation. Indeed, in reality, these factors, national factors, typically depend on energy and construction policy, and for example, these factors for renewable fuels are typically selected between non-renewable factor, which can be very close to 0, and total primary energy factor. So it's something between 0 and 1, depending on the country. For example, in Finland it's 0.5, in Estonia it's 0.75, in some countries it's 1, and in some countries it can be 0.2. So there is a lot of fluctuation in these factors in all over Europe. Well, this technical definition indeed specifies detailed system boundaries, and as the target is to calculate the delivered energy and exported energy, we have these outer system boundary that follows the building site, and this is called the system boundary of delivered and exported energy. But in the energy calculation, we need to start from energy need system boundary, where you will calculate a theoretical need, for example, for the heating energy to keep a fixed temperature in the room, and same for the cooling, take into account the lighting appliances you need to have in the building, domestic hot water, and where this calculation is based on gains and heat losses, both solar gains, internal heat gains, and provides end result as energy need for heating. So it's just kilowatt hours thermal energy needed to keep the temperature. Same for the cooling, electricity for lighting, electricity for appliances. And after that you need to start to calculate energy use in building technical systems, what means all the HVAC systems. And in this system boundary, you are able to distinguish between HVAC systems and between on-site energy production, because you calculate all possible technical systems you have in the building, and where you know how much is coming from these on-site renewable energy production and how much energy is used in building technical system. For example, heat pumps are calculated as a part of a building technical system, a part of a heating system, but solar collector can be calculated separately. When this calculation will end as required delivered energy flows, how much electricity and fuels you need, and what will be exported energies. And if you proceed to that final system boundary, you cannot anymore distinguish between on-site measures and renewable energy sources, energy produced from these. But this is still 100% physical and scientific calculation, indeed, where depends on national calculation methods, national input data, climate data, so on, but still this is 100% of physics. And when you continue to calculate to primary energy, so you have these national primary energy factors, when these will take into account national energy policy, construction policy issues, and this calculation is not anymore 100% physical, because these factors are very seldom have 100% physical background, but they are very much driven by energy policy. So in the original definition, we have did some revision. There is another directive, RES directive, renewable energy sources, what requires to calculate the contribution of renewable energy used in the buildings. So we call these RER, renewable energy ratio, and it's additional indicator to the primary energy indicator, and now this indicator is also addressed and equations given for that. We have addressed the question of the time step. So basically now we say what you will need to use hourly calculation, which is basically a dynamic simulation, in order to be able to calculate exported energy. because you need to know energy flows in every time step, and this time step should be quite short in order to be able to say how much on-site, for example, on-site solar electricity can be utilized in the building and how much is needed to be exported to the grid. So we see that in the future these energy calculations will be based on dynamic simulation, and this will be only possible approach if you have on-site renewable energy sources and you will export something to the grid. Also, we have added additional CO2 indicator, which another alternative indicator not required by the directive, but if you want to calculate the carbon footprint of a building, you will need also this indicator. And there are some improvements in the definitions, no major changes. We have also addressed the sites with multiple buildings. For example, universities represent typical property owners having one large plot and a lot of university buildings, and then you need a guidance how to calculate primary indicators for this type of building sites. We also addressed this load matching and grid interaction issue, because when you have on-site electricity production, there is a grid interaction between the building and the grid. Well, and these definitions are very similar to original ones, but there are only some small improvements, and nearly zero energy buildings are defined through net zero energy building, which has exact performance level equal to 0 or below. And as defined that it can be minus, it means that net zero energy buildings will cover also plus energy buildings by this definition. And but the important it is the maximum value equals to 0 kilowatt hours per year per square meter primary energy use, and then based on this you can define nearly zero energy buildings, which are actually quite complicated to define, but is done so that such buildings are technically and reasonably achievable with national energy use which higher than zero primary energy, and will be achieved with a combination of best practice energy efficiency measures and renewable energy technologies, which may or may not be cost optimal. And this cost optimality, especially for these renewable energy technologies, depends very much on national incentives. If you have some support for these technologies, then they are profitable. If not, they are not cost optimal. So in this definition, you can take into account national conditions, and both of these definitions, it is important to notice, they operate with annual balance of primary energy. So it means that the building can still be grid connected, and you can use delivered electricity for the grid, for example in the winter time, if you are able to feed to the grid in the summertime the corresponding amount of electricity, and then you can be net zero. You can have net zero energy balance, and this is called net zero building. So this is not the discussion of off-grid buildings. That's something else. The purpose of a directive is to have on-site production and to support with this centralized energy production. But both are indeed needed, and centralized energy production is very important. And this also means that depending on national energy system, every country needs to be careful with national measures so that all the performance of a national energy systems would be supported by these new nearly zero energy buildings, and you will not cause any technical problems or conflicts with national, for example, incentives and solutions. Indeed, that's a very complicated question. But basically, there are many analyses available all over Europe, and these show that, for example, solar electricity typically is not a problem for the centralized production. It's typically will support and will reduce the peaks. Wind production can be more difficult for the energy system, but there are technical solutions how to overcome these problems. And this is basically, indeed, it's a political decision taken by us in Brussels for all European Union, and that's the way to proceed. And we want to have, when you construct new buildings, they need to be highly energy efficient, and they need to compensate their energy use with on-site energy production. That's one way how to reduce national primary energy use, and typically has a positive effects on CO2 emissions as well. Well, I will show one example what it means, the primary energy calculation for such office building which has nearly zero energy performance. It's located in Central Europe, in Paris, so heating is not an issue in this building, but it has a gas boiler for some heating needed. When the cooling is much bigger issue, and there is 1/3 of the need is covered by free cooling and the rest with mechanical cooling, there are given these COP values. Ventilation system is mechanical ventilation with heat recovery, so with this input data, and there is also a solar PV system in the building. So with energy simulation, you are able to calculate these net energy needs, and these are basically the input data for this example. So this building will need this amount of heating, cooling, appliances. For the appliances, what's basically input data for the building regulation, because typically does not depend on the designer's choices, but fixed values are given, and lighting indeed depends on the solution applied. To cover this net energy need, you have a building technical system, for example, heating with a gas boiler. 90% efficiency will give you this amount of natural gas needed. And when you calculate all electricity needs, so free cooling was calculated by COP of 10, so you need very little electricity. Compressor cooling with COP of 3.5, a bit more. Ventilation was given. Appliances, it's a fixed value, and lighting, nothing will change here. And the sum of all electricity use is 39.8. And now you should reduce on-site production. There is a solar PV producing 15 kilowatt hours per square per year, and from this it is said that you can utilize 6 in the building, and the rest you need to export because there is no load when this production is available. So, and this will mean that from this sum of electricity, 39.8, you can directly reduce with 6, and you end up with 33.8 delivered electricity, and the rest 9, it will be exported. And that's the final delivered and exported energy balance for this building. And now you can take national primary energy factors and calculate the primary energy. It's given here. If primary energy factor for the gas is equal to 1. That's typical for the fossil fuel, and for electricity it's considered 2. So that's natural gas. This is delivered electricity and minus exported electricity, and the same primary energy factors are used for delivered exported electricity in this example, and the end result is 54 kilowatt hours. And this is quite typical that these buildings will have primary energy values between, let's say, below 100. In Central Europe, you can have smaller values. In North Europe, they are more close to 100. So it means that nearly zero is not so much close to zero still, because of technology available. We are not able to go, for example, in office buildings exactly to net zero. In residential buildings it's more easy. For example, in houses you have a lot of roof surface when you can install a lot of PV, and you can end up with zero. It's not possible, but to have a high-rise office buildings you have much more limitations, and you need to operate with higher values. Well, this is one answer. So the primary energy is calculated in that way, but if somebody will have a question, how much of the energy use of this building is from renewable energy sources, then indeed you see that there are some solar photovoltaic. This is renewable. When we speak about free cooling, this could be renewable. It is from outdoor air basically, so from this value you can calculate how much is renewable energy. And indeed renewable energy, something in the centralized energy production can be renewable fuels, so some percentage of that energy can be also renewable. And if it would be a biofuel, this indeed can be also renewable energy, but in this case it was a gas, so a fossil fuel. It means that you need basically another calculation to calculate this renewable energy contribution, and this is one requirement of RES directive, which basically operates with energy production issues, but there is one chapter for the buildings with basically with this one very specific requirement. And for that purpose, the same energy balance can be still utilized. We are looking for on-site renewable energy sources when we have the same delivered energy and exported energy flows. But what we need to take into account additionally are everything related to heat pumps, because these in the energy calculation were calculated as a part of a heating system with relevant coefficient of performance or seasonal performance value. But now we need to know how much ambient energy, how much thermal energy from ambient sources these heat pumps or chillers will take, and this is needed to take into account. So this is the only new term in the system boundary for this renewable energy contribution. And basically we speak about ambient heat exchangers of heat pumps, and to take this into account. And in the case of a free cooling, where you do not operate the compressor of a chiller, this is also ambient thermal energy taken for the free cooling. So this can be taken into account. So there is an equation given for that, but I will show an example. It's much more easy to follow. It's for the same building with all the same energy flows already calculated, but now we need to take into account this free cooling from outdoor air. So free cooling was produced so that condensers were used, so the fans were operated, but the chiller was not switched on in the free cooling mode, and we take these into account, have an additional term. Basically, we have this 15 from photovoltaic is here, and this is because of free cooling. And then we consider that 20% of the grid electricity is renewable, so this 20% is taken into account here. And then we need to divide this to sum of all energy flows coming into the system boundary. So these are once again the same as here, and then we have this fuel, fossil fuel, fossil grid electricity, so 80% of the delivered minus this exported energy, and we end up at about 54% of energy used in the building is renewable from renewable energy sources. And regarding this calculation, we still have ongoing discussion with European Standardization Organization (CEN), because they have proposed that in this calculation you could also use primary energy. So it means that every term you need to apply a total primary energy factor, and this indeed will change the result. But it's difficult to see that there will be any general principle to say that this calculation should be based on not weighted energy flows as it is in this case, or it should be based on primary energy. It depends on the purpose, and depends on the choice what will be the way to calculate that. Most likely we will add to our document an alternative equation where you can calculate this renewable energy ratio with primary energy factors. And these factors will be total primary energy factors, meaning that also this solar energy will have a factor of 1. And indeed, when you need to apply also total primary energy factors for the electricity and so on. But this is ongoing discussion, and it is very difficult to end up with one single equation regarding to this question, when it is much more clear when we discussed about the primary energy indicator. So it's difficult. It has even some fundamental difficulties. What's the meaning of renewable energy contribution in the building? Indeed, it is one solution to reduce primary energy, and if you see primary energy as a final target, then this is only one measure to achieve primary energy reduction. But in the RES directive, it is seen as specific target. So it's we can even say that in Europe we have these issues a bit over-regulated. We have too many directives and so many targets that it is not easy to follow by the engineers and when to say what you need to do nationally. Basically, this can be interpreted also so that this renewable energy ratio, this is not so strict requirement as this primary energy indicator. Primary energy indicator is something you really need to have because this is in the definition of nZEB buildings, but this is something complementary indicator and can be defined in many ways, and I can see that there will be a lot of different national definitions for this indicator. It is not so. It has not so clear fundamental basis compared to the primary energy indicator. Well, we have addressed the building sites with multiple buildings, and in such a case, typically you have some site energy center so combined heat and power production operated with biofuels or fossil fuels, whatever, and when it is difficult to distinguish what share will be for a single building, but basically primary energy indicator requirement by directive, when you can operate still with a building site boundary and you are interested how much you need delivered energy and how much energy is exported and what will be the share of each building, that's not anymore so important question, because you can treat this building site as one entity and to calculate one primary energy indicator for all buildings. Indeed, it has to be divided by the sum of a net area of these buildings, but maybe described by one single indicator. So it follows 100% the definition given science now, but now you can just add energy use of all buildings to sum these and to reduce on-site energy productions, and then the calculation is exactly the same as it was for a single building. Well, in REHVA we are coordinating this work with CEN, and as I said, CEN started the revision of EPBD standards. There is a specific mandate, a specific work for that purpose, and the second generation EPBD standards will be prepared, where most likely will be more than 40 standards once again, and it's a huge work to revise all of these standards. Indeed, there will be one major standard called overarching standard with all of these definitions, and for that standard this REHVA definition has been very important input because since now it has been only available methodology, and indeed it is utilized in the CEN, so we have really had two-way information change with CEN, and we hope that even the symbols and specific technical definitions we are able to harmonize. Indeed, the work we are doing in REHVA is much faster. We are able to publish our revised definition next year, but it will take much longer for the CEN to publish these standards, because it's a long and slow process where every member state has basically to accept these standards. There are voting procedures and all of these CEN procedures, which means that it cannot be very fast. But in REHVA we can have much faster track. So actually this REHVA definition will be very soon revised, and we are preparing right now a final draft and expect to publish the report in February next year, and from the January it should be already available from the REHVA webpage. And to conclude these definition issues, I can say that the original objective of REHVA definition does not need any revision. It was intended, and it is still intended, to help the experts in the member states in defining nZEB buildings in a uniform way, so that the local conditions can be taken into account, but the uniform methodology will be used. Can be seen as a proposal for the uniform implementation of EPBD in member states, and the proposed technical definition for nZEB buildings which follow EPBD recast and cost-optimal regulation. And the most important, I think, that it provides energy calculation framework and system boundaries which are prepared in the level of a detail so that they can be implemented in national building codes for the primary energy and renewable energy ratio indicators calculation. Because in every country you need to revise your building codes or regulation, and then this kind of very technical, detailed level equations and definitions are indeed needed. So then I will proceed. If you have any questions regarding to these general principles, nZEB definitions, you are welcome to ask, and I will move to another part of lecture dealing with nZEB buildings and case studies. And as you know, there are already many pilot projects across the Europe which very often are called nZEB buildings, sometimes net zero, sometimes nearly zero. Indeed, there is a variation in the definitions and performance levels because these definitions are very new. Methodology is not established yet. There are indeed many countries currently are working with national regulation, and these definitions will be included, and in future we hope that this is more harmonized. But since now, when the design of these buildings maybe has been started 5 years ago, and it's a long design process, construction process, so you cannot expect that you can very easily compare the performance, reported performance from the energy simulations or measured performance from these buildings. It's very complicated. As it is very complicated to compare energy performance requirements between different countries, it's almost impossible. But hopefully in future we have more harmonized definitions and requirements. And at least EPBD requires the primary energy indicator, so basically every member state has to move in some time period to the primary energy. That will make this comparison more easy. When we speak about the nZEB buildings, sometimes you can expect that they can be extremely complicated. That's one way to see how nZEB can be designed and constructed, and indeed this can have some implication in operation and maintenance phase. But there is another trend that can be also seen, that simple and reliable solutions are looked for and developed in order to provide this high-level performance, and typically they are based on high-efficiency components and careful system design. So there are, you even can say that, two competing trends in this field. And to analyze, for example, office buildings, you really need a simulation tools to use because these monthly calculation tools, in many countries still official calculation tools, have provided very often too optimistic results. So these tools easily assume better utilization of internal and solar heat gains than it will be in reality, and can assume less system losses than it is reality. So these are not so reliable. You really need to have a detailed simulation when you can see what's the performance of such buildings. There are some buildings what are reported in in REHVA journal, and these results from these buildings follow the REHVA definition, so these can be compared. These buildings are, this is from France, Finland, Netherlands, and this is from Switzerland. At least these 4 buildings are, you can download when you check these numbers of the journals from the REHVA web page. which is available for everybody. I will now show two case studies in more detail. One is from Central Europe, from France, another from Finland. And you will see that some technical concepts will be similar and suit for both climates, but some concepts can be very, very different and depend strongly on climate. I will discuss simulated and measured energy performance. Both are available from a building from France. In Finland it's still based on the simulated, it's a new building. And also the issue of extra cost caused by nZEB. There is a data for these buildings available. And then I tried to show what have been the key technical concepts based on these and other buildings needed to achieve this nZEB performance level. So this is building from France. You can see that a lot of architectural design has been done. For example, the building has no corners. It will reduce the area of the building envelope by about 10%, not to have corners. And it's a strong contribution by the architect. So all the roof is covered with photovoltaic. And when you see also that there are large windows for the daylight utilization, this will not work in cold climate, but works very well in temperate climate we have in France. And you also see that there is a large semi-transparent solar protection shield. It's fixed, but it's with some enables to go light through, but provides a solar protection. So in all cases in such high performance buildings, you need to start from the architecture, from the massing, and from architectural measures in order to be able to have an effective end result. So this is the interior. It's like a typical building, nothing special. Maybe what you can see here, there are chill beams installed and lighting. And construction cost, they reported from France, is quite reasonable, 1,400 euros per square meter, and they claim that this equals to the standard building cost for the standard office building in France. So with a careful design, they claim that no extra cost has not caused in this case. Might be difficult to believe, but when you take a look about the building envelope solutions, you see very, very moderate values. So it says that in the Central Europe, you don't need so specific or overkilled technical solutions to achieve nZEB performance level. Rather, you need a very good integrated design, and this does not cost a lot of money indeed. So this is one explanation how the cost can be very reasonable. So it's more an issue of a client. Client needs to have an ambition to construct such building, and when you need a very good design team with capability for the cooperation and integrated design. So this facade design is quite outstanding. It will maximize daylight and at the same time provides good solar protection. Technical systems are quite typical to these ones we are using in North Europe, so mechanical balance ventilation with heat recovery, room conditioning with chill beams. I think these are also common here in Latvia. But some extra features are night ventilative cooling is applied so that there is a central exhaust from the atrium, and you can have fresh air from the facades, and there is also adiabatic cooling is supporting compressor cooling. Because of very careful daylight design and large windows, very small installed lighting power is achieved. But this is indeed, it is not enough for the all lighting, so task lighting is also installed and advanced controls are used for the lighting. So this shows the operation principle of this night ventilative cooling. In the daytime, the system is operated as conventional mechanical ventilation system with heat recovery, but in the summertime you can boost at the night time the ventilation with low pressure fan from the atrium, and there are intakes in the facades you can see here almost in every room. That is indeed mechanically very complicated facade solution, because you need to have actuators, and all of these will need maintenance and so on. But hopefully this will work in this building. Indeed, you cannot say that this is a simple and reliable solution. It is something else. It's very advanced and complicated solution for this nighttime ventilative cooling. Then the energy balance of the building. Energy needs are not reported here, but you can see delivered energies, very little for the heating. So it's you will need to move by 1 decade if you go to North Europe, but in Central Europe heating is indeed it's very little. Because of effective free cooling solutions, electricity need for the cooling is also quite low, but this is already electricity used by compressors. When fan electricity, pumps, lighting, elevators also taken into account, and you see that appliances are not so much as they commonly have, and then quite a lot of PV production. So this is exported, can be some of this is exported energy, not all cannot be utilized in the building. That's the reason it has a minus mark in the energy balance. This is French primary energy factor for the electricity, 2.58, and this is for the wood fuel. And you end up with primary energy. So that designed is 24, but measured is much higher. And the reason is here. All the other energy flows, basically they are, indeed there is a bit more heating than was calculated by the simulation. Maybe some problems with these facade openings can easily cause this. You overcool and you need more heating, but still it is not much in the primary energy when you need less for the cooling than it was predicted based on the measurement. So fans very well correspond to the predicted, and also pumps a bit more, lighting is very well predicted, elevators very well. But what was not well predicted are just these office appliances, so meaning all the computers and office equipment, because this number is extremely low and cannot be easily achieved in a practice, and you can see that in reality it has by factor 2 or even a bit more higher. Still, this number is very, very low, and indeed a good performance shown in that building. And it shows that when you have so effective technical solutions, really these appliances can be a major issue in future buildings, and somehow you need to use computers using less electricity and more effective or other more effective appliances. So another building I will show in more detail. It's from the cold climate. It's from Helsinki, Finland, also reported in the REHVA journal. it's quite new building, was completed last year, and it is also office building. You can see here it looks like a glaze building, but it is really not. It is only a double facade here, and there are normal, quite small windows behind that double facade and well insulated building envelope, and all other facades. So this is facing to south. All other facades are not with double facade, are common ones. So in that case, construction cost is something else. It is very expensive. Cost level in Finland, 2,400 euros. And they also calculated very carefully what will be extra cost because of these nZEB measures. And they ended up at about 0.5 to 0.7 million, depending how you compare which will be the reference solution. It is actually not so easy even to calculate what will be the extra cost, because when you have a building project, you have just a budget and you have a cost, and it's difficult to say if some other measures would be used, what will be the cost being for the reference solution. So that's the reason for some range given here. But it means that still the extra construction cost in the cold climate has been from 3 to 4%, and actually it's from 70 to 100 euros per square meter. So it is not so that bad. Key solutions in this building, it also has a lot of architectural measures and very advanced technical solutions, however quite simple technical solutions. So PV production in the facades, so it was already, there is a facade integrated PV cells and something on the roof also. Then the building will use a district heating, that is very typical in Finland and other Nordic countries, also here in Latvia. It has air conditioning and balanced ventilation with heat recovery, but all the cooling for the air conditioning is from the boreholes. There is no chillers in that building. So it means there are a lot of boreholes, each 250 meters deep, and cooling system is sized for quite high temperatures, 15 flow temperature and 20 return temperature, both used in air handling units and chill beams in the building. Now I'm sorry this is in Finnish, but to show these architectural measures I have only a couple of slides in Finnish. This shows that the architect did a lot of facade designs to see what the shadings and how to have relevant solar protection and how to have maximum daylight. And indeed these are very well known design principles to shade in the summertime when you have solar angle is higher, and when you have in the winter time to make it possible to have to utilize solar gains. This is very basic. It's basically done in every building. But when they try to find some solutions for to boost daylight and used such reflective surfaces here on the bottom of the windows, which will increase some daylighting. Indeed, if you have some solar protection to protect the glare, this might not work. But in the rooms where this glare is not so big issue, this can work. But it shows these are the question to be addressed in the design, and indeed there are many technical answers, many technical solutions, but it is important to address these issues. This solution is very interesting, and it refers to the massing of a building. You can see that this building is very deep, So it has a double deepness compared to similar building, and this is done by the inner courtyards. This is an inner courtyard. Also, you may call this atrium space. And you see that the rooms have the windows to this inner courtyard. And this is covered by the roof. There is a glazed facade and some roof windows. So this makes it possible to have very deep building and to improve the compactness and to reduce heat losses indeed. So now I will show a view from that courtyard. You are looking out. You can see that there is a glazed facade to provide lighting, and the windows of the rooms will continue in this direction. And the roof is also has a special surface to reflect natural light, and there are only a limited amount of roof windows. Actually, all windows are vertical. So this is very specific design measure for the cold climate and very effective ones. And actually the building has 2 of such large courtyards with the windows to the inner courtyard. This allowed to reduce heat losses, and indeed it's very demanding solution from the architect. So architect really needs to work with alternative solutions and to find, to be aware of effects on the energy use. And this is very good example of the integrated design. You really need to have such nZEB buildings. When I am jumping back to the technical systems, you can see very large air handling units. And when you have large units, you can have very low specific fan power. So you use only a little electrical energy to run the fans and the ventilation system. And also another point, in the large air handling units, you can have better heat recovery efficiency. So the temperature ratio is about 80% in this case. And ventilation air conditioning system is very typical, used in Nordic countries. So it is served by district heating, which will go to the radiators. There is the radiator heating in all of the building, and also indeed you have heating coil in the air handling unit. And then for the cooling, there was used a borehole water. There is even no heat exchanger. This is just a water tank, and you circulate this borehole water to cooling coil in the air handling unit and to chill beams in the rooms. So very simple operating principle. And when you have a large air handling unit, you can have use high efficiency components and achieve very low energy use. Actually, it was a constant volume system for office rooms and demand controlled ventilation. So there were about 5 air handling units and the separate air handling units for the demand controlled ventilation system for other rooms which are not constantly occupied, as for example open plan office or office rooms. So this was also used. What's very specific, it should be a world record heat recovery from the toilet air with 80% of heat recovery efficiency. And it was done with rotary heat exchanger. It's typically not allowed to use rotary heat exchanger to recover heat from the exhaust of the toilets. But as the supply air were directed to the toilet block back, when actually no problems are not reported from this building, and this shows that because there is a lot of dilution in such an air handling unit, serving all the toilets, and the orders have not been a problem. Indeed, you can do this with plate type of heat exchanger, but here the designer wanted to demonstrate that even the rotary heat exchanger in such application, it would be a possible technical solution, and feedback has been positive since now. If you have a plate heat exchanger, you need a much larger air handling unit to achieve the same heat recovery efficiency, or you need to use a smaller value, which is also indeed possible. In the room side, you see for the room conditioning, these are active chill beams, so they both serve supply air and cooling when needed, and there is a conventional lighting system. It's not the LED lighting, but this is with these conventional T5 lamps. Still the install power is quite low. And actually the lighting is also one new question for HVAC engineers. You need to be able to understand and to cooperate with electric designer in order to find relevant solutions for such high performance buildings. So the energy balance of this building.
Very good.
Yeah. So I was saying that when you compare to France, really space heating and ventilation, it is by factor of 10 what's very typical to the cold climate we have. And this is energy need, and delivered energy is even more because of some system losses you have in the heat exchangers, and distribution losses carefully calculated in this case when these numbers are much higher compared in France. In France, they just calculated that this for the heating it's about 2, and they ended up when they measured it's 6, and indeed they also have all the distribution losses and issues like that, but they are not so familiar to calculate these. For example, in Finland, according to the building code, you need to calculate all these distribution and emission and generation losses to take these into account. So this is district heat, hot water. It is a little bit, and actually this is the code value when it's the input value you use in the calculation input data. You cannot affect these by the design. Indeed, design solution means that this is done by district heating. When the cooling energy need, it's almost as much as in France because of this low solar angle we have. A bit little, but as this was done by the borehole cooling, it's not much. You need only 0.3 electricity for the circulation pump. That's the only delivered energy used to cover these energy need. When fans and pumps, lighting, appliances, now it is much more realistic figure here, and it's from a Finnish building code. It's also input data. Lighting is indeed calculated, and also this building has some PV installation. So on the south facade and on the top of the roof, providing this amount of solar electricity. And it ends up with 85 primary energy, so that these are Finnish primary energy factors, 1.7 for electricity and 0.7 for district heat. So which are the most challenging technical solutions you have in this kind of high performance buildings? I tried to show most challenging one related to the design and especially regarding to HVAC systems. Maybe the first issue, as we discussed, that it's highly important to have integrated design and to have architect who will understand all the selections he is doing, all the choices, what will be effect on energy use, and starting from the building mass and the shape of a building is very important. and when you can end to the fenestration design, so to the facades. And these facades really need a special consideration, especially in office buildings, because they affect lighting, and you need to consider interactions between daylight, solar shading, heating, cooling needs, and electric lighting need. So basically you need to do a lot of simulations, and then you need to calculate, first to calculate energy needs, and then you end up with delivered and primary energy depending on the system solutions. And if carefully done, you really can take some advantage of internal load and solar heat gain reductions achieved. And it's evident that this architectural design needs to be coordinated with mechanical design in order to take this advantage. Also, as I told, this electric lighting is quite a new issue for HVAC engineers, and you need to cooperate with electrical engineer in order to find relevant solution, and also architect has a role in this process. Basically, it's well known if these occupancy sensors and these photocell controlled dimming is used in order to provide lighting level only needed, and not to have lights all the time at full power and overlighting, then you can save a lot of energy, electrical lighting energy, especially in the perimeter zone close to the facade, and somewhat less in the second row, which has a longer distance from the windows. I show one example. It's an Estonian building, unfortunately. Not nZEB building, will be only low energy building in the design process. And for these buildings, we studied high performance facades with very good glazing options, U value of the glazing 0.6, and light transmittance, if it is a single facade, 71% light transmittance. So these shorter facades had just the conventional walls, and these longer facades had a double facade. So, and in that case you lose something light transmittance because there is additional glass, not affecting U value but blocking natural light and providing somewhat better solar protection, so the G value. So these are exactly the same for both cases, and these results are for the window to wall ratio 25%. You can see that net energy needs for the heating, it's dominating, about 23. For the cooling you need 8, and it is also energy need. There is no COP or system is not taken into account. And for the electrical lighting it's 8.3. Indeed, this is calculated with this installed lighting power, but when you can calculate with a building simulation tool, depending on your facade solution and the control solution for the shades and lighting. When you increase window to wall ratio from 25% to 50%, actually that was the wish of the architect, then the results are the following. You see that you will need much more heating, somewhat more cooling, and as the architect argumented that you can reduce electric lighting. Yes, you can reduce from 8 to 6, but this evidently does not compensate these increases in the heating and cooling. Indeed, this is electrical energy and has a higher primary energy factor, and depending on the systems used here, these will have lower primary energy factors, but in any case, in a cold climate, you are not able to compensate. And basically the calculation is that you need to provide a system calculation in order to calculate delivered energy, and then to calculate the primary energy, or energy cost to take a decision what will be the right solution. But this is very typical facade optimization process in such high performance buildings. When indeed this is just an idea how to utilize more daylight, you can see here some parabolic concentrator. It's certainly not suitable for the cold climate, but works very well in Central Europe and can provide very nice natural light conditions where there are internal blinds and no glare in the office desks, but good lighting level in the room and with very small installed lighting power. Similar solutions, I don't think that this type of solutions, it will be covered with half of meter snow right now, will work in cold climate, and indeed these light shelves will increase a glazed surface, which is not good either, but something to find for the cold climate can be very good research question. What will be suitable solutions in our climate? But this is very nice for Central European climate. Then I will proceed to one of my favorite topics regarding the ventilation systems. And as you know, in a cold climate you need basically heat recovery. So it means you cannot avoid mechanical ventilation because with mixed ventilation solution or hybrid ventilation, mixed mode, how they are called, you are not able to achieve heat recovery effectiveness close to 80% or even more what's needed in our cold climate. So basically you need to have mechanical system. You can have some other operation mode for the summer period. For example, in atriums you can use window openings, whatever passive means, but in the winter time mechanical system is basically must. And mechanical system can be very simple one. So if you use a constant volume system, so this shows meeting rooms where you need some controls, but in offices, basically in a simple system you don't need any controls. Or you can have all air system with many actuators and dampers and so on, much more complicated VAV system. These both show the centralized system. Also it's possible to have decentralized system. So it means that this is one example of decentralized intake from the facades. So the supply air is provided by such an air box containing a filter, heating coil, cooling coil, fan in every room, and in such a case you don't need any supply air ductwork, no need. But indeed you still need some ductwork for the extract air, which is so still the extract ductwork, which is still a centralized one. And this is one of ceiling panel application used both for the heating and cooling, so provides radiative heating or cooling, and is quite much used in Central Europe, less used in Nordic countries because we have preferred to use radiators below the windows for the heating, and in that case we don't want to invest to so large panels, and it's easier to use chill beams, somewhat cheaper solution, what has been typical in Nordic countries. So basically in such a system you indeed have a limitation regarding the heat recovery, because you need to use from exhaust and have some sort of exhaust air heat pump to do that, and you have a lot of these air boxes to maintain. So it's extremely complicated system when you account how many maintenance points you have in such a system, and indeed it can be a disaster in the operation. So that's the reason especially in Nordic countries, the debate is about how to use effective centralized ventilation system. And as a traditional system with many components and very typical reduction and higher pressure losses, we are debating should we use something larger and more simple and more reliable. This can be called final pressure drop ventilation, so that all the balancing are done with with diffusers, which can be also ceiling beams, whatever type of supply air terminals. And for such system, you really need 1-2 step larger air handling unit, so it is really larger than this one, and you need a larger ductworks to have very small pressure drops. And when in such a case, if a pressure drops is very little, you can use also a constant volume system, maybe in office rooms, not in office rooms, but in meeting rooms, where is a variable load. Indeed, you need controls, but all in other rooms can be constant volume system, and you can go to very low specific fan power and indeed have high heat recovery efficiency because of these large air handling units. This is one sizing example of such system. So the conventional system operates with around 300 pascals pressure drop for the ductwork, but a low pressure system, constant pressure one, operates with around 110 pascals. So that there is only 10 pascal difference in available pressure, or 20 pascal from here to the last diffuser. And in such a case, there are no need for the silencers. Large air handling unit is so quiet, nothing, sound attenuation is not needed anymore, and basically no need for the dampers, no dampers here, only adjustment by the supply air terminals. And this really is very, very simple, and you can believe it's also reliable to operate such a simple system. When in cold climate, maybe these cooling issues are not so severe. Actually, we can reduce very easily cooling load by having a relevant, let's say, relevant window size and solar shading options. And we can do this kind of buildings with common chillers. You can select indeed with better seasonal energy efficiency ratio. There are available many molders in the market, and the range of so-called ESEER values, so European seasonal energy efficiency ratio values, is quite large. You can select from 2.5, let's say, to 5.5, depending on the chiller, and then you can use very conventional system, but once again based on high efficiency components. In Central Europe, where you need much more cooling energy, where more advanced solutions are indeed needed, and one example is such a solar-fired absorption chiller, so that you use the solar collectors to provide heat, most of the heat needed of the chiller, and the rest can be provided by, for example, by the gas, if this solar heat is not enough. But very typically this can be enough, because cooling load and solar load are typically very simultaneous when you have solar radiation, when you have also a cooling need, and can be very effective system. So maybe this is a good example, but not so relevant for the cold climate. So to conclude, what have been the common solutions used in nZEB office buildings? Indeed, in every building we have seen a lot of demand reduction measures, effective systems, and on-site renewables. All these three components are needed. When we want to say something about energy sources, we can only say that there is a full variety of energy sources used, no rules regarding to these. Heat pumps, district heating, bios, CHP, solar PV and thermal, depending very much on the building location, on the building site. So it always a question what will be the best energy source. It's very building site dependent question. Heat recovery ventilation has been a common solution both in Central Europe and indeed required in North Europe, and often has been demand controlled, centralized or decentralized systems, sometimes combined with natural stack effect ventilation for ventilative cooling purposes. Free cooling solutions have been typically used, and these typically support mechanical cooling. For example, in Finland, where the ground is mostly a granite rock, it's easy to have boreholes. So boreholes are very popular in Finland, Sweden, Scandinavian countries, and they have also available district cooling systems. But in Central Europe, you need something evaporative or ventilative cooling solutions or something else. Optimized building envelope, in all cases, in both climates, indeed the solutions are different. Utilization of natural light, yes, no other way to reduce electric lighting demand. High efficiency heat recovery, low specific fan power needed in all climate. And then you indeed can use demand controlled solutions. Especially in cold climate, you need a water-based distribution system for the heating, because circulation pump is using much less electricity compared to all air systems, where you will need a significant contribution of fan energy if you try to use air heating. And it seems to be the same for the cooling and for the heating. So the water-based system have advantage, and indeed there are available a heat pump system based on the refrigerant, which is something similar to the water-based system, very effective can be, and specifically these variable refrigerant volume systems are very effective. That's an alternative to these water-based systems. And indeed, you need to utilize thermal mass and other passive measures to have a good integrated design. If you do all of these, then the office appliances will dominate in your energy balance, and this is another problem to be solved in future. But for this problem, we have Eco-Design Directive and other directives with these energy certificates with ABC for all kinds of equipment using electricity, and these appliances, I am sure that they will develop so that the electricity use will be reduced in future. But now we can say that building technology and HVAC technology provides even more effective measures than we have when we compare to the office appliances. It's not so easy to select very effective office appliances when you look at the final energy balance of such nZEB building. There are some guidelines. This is from the REHVA guidebook for the sustainable office building design, and there are some recommendations for low energy buildings and for nearly zero energy buildings. Some indicative values for key design parameters can be found from the guidebooks, and indeed these are very good to follow in the in the scoping stage and the concept stage of the design, when the energy simulations are not yet available, and to find relevant solutions, and then to proceed to more detailed design. Then it would almost conclude my presentation when you compare common solutions in Central Europe and North Europe. You really can see that in Central Europe you will need large windows for a maximum daylight, and then you can save lighting electricity. In North, as here in Latvia, you need as small windows as you can have so that you can maintain relevant daylight factor, and then you can reduce heat losses, and this will compensate with electrical lighting. So in Central Europe you will need only very little thermal insulation compared to these insulation levels we need here in North. As good windows as are the possible products in the markets, and indeed also very well insulated walls, especially in residential buildings. In office buildings usually the wall surface is not so much, and most is from the windows. In Central Europe you need much more cooling need compared to the heating need, but in our climate you need slightly less cooling compared to the Central Europe, but a lot of heating, so almost by factor of 10 compared to the Central Europe. So external solar shading is very effective, most likely in both climates, and we have a special program of very low solar angle. In Central Europe you can easily have so-called glass buildings if you use external shading, solar shading, but in our climate you need to reduce glazed areas, so that means you need to use double facade solutions to have a building which will look like a glass building. But if architect would like this, then this is technically possible. Indeed, these double facades are a bit more expensive compared to a single facades. Free cooling needed in both climates to support compressor cooling, and in a cold climate you even can produce 100% of cooling energy, for example from borehole water. It's possible, but in Central European climate you still need the compressors and then something supporting the compressors. And this water-based distribution system, especially for cooling in the Central Europe, because there is a lot of cooling, and in our climate for both heating and cooling. And exactly the same solutions are heat recovery ventilation, no difference between the climates. Demand controlled ventilation and lighting provides the similar type of savings, and PV panels can be used in both climates. And actually, as you know, that solar radiation sum is equal if you take Latvia or Estonia, is something like it is in North Germany. So availability of solar radiation is not limited here in North. Indeed, there are much better locations, but when you compare inside the Europe, we are quite the same as North Germany, and they use a lot of solar PV, so no reason not to use cannot be found also here in North Europe. And finally, indeed, to design such high-performance building, you need different design process. Energy simulations have to be included already or in very early stages, and they should include this daylight simulation so that you can compare massing alternatives and so on, and should be started already from the scoping. It means that the design team cannot consist only from architects, but you will need engineers in very early stage to carry out such integrated design process. And what has been a problem, a real problem in such a building, it's difficult to reserve enough space for mechanical rooms and risers, so for the ductwork. And if this is not done in a very early stage, you cannot find this space for the systems anymore at the later spaces. So this really needs to be considered. and for the effective air handling units, they are quite large and they need a lot of space. When you conduct the simulations are not necessarily very complicated. You can take just one typical floor and to conduct a lot of simulations with very many parameters varied for such a simple one floor model. And this is enough for most of the decisions in the design. And at the final stage, indeed, for the building permit, you need to conduct more complicated simulation in order to calculate the final primary energy indicator, for example, to apply a building permit. But in the concept stage, very simple simulation models can be used, and these simulations are also very fast. And indeed, you need to optimize the facade, as was discussed, so that you find relevant combination for daylight, solar protection, cooling and heating, and electric lighting. And indeed, it can be recommended that first you need a careful verification before handing over the building, and this means careful commissioning procedure. And typically all countries have problems in this stage because there are the deadlines and no time to tune the system, to test, to commission. That's very difficult issue in practice, and this can be made more easy if you use very simple systems. When all these operation, maintenance, and also verification and commissioning is much more easy, and this really can be recommended from the operation and maintenance side of the buildings, or the building managers will like to have very simple and reliable solutions. I prefer this trend, not to do overkilled buildings with very complex solutions. That's indeed another trend, but I think this is something we really need to avoid in order to make these buildings also easy to operate and to have satisfied occupants in these buildings. Thank you very much. Well, please.
We speaking about energy use requirements of the buildings and cost efficient, cost optimal.
Yes.
But if we force countries and force our society in Europe to satisfy those requirements, perhaps it will be done by a wrong way, in spite of requirements for indoor air quality and thermal comfort. Increase the amount of sick building.
Yeah, that's indeed, and this also attributes to these very complex buildings, when you can have systems are not operating as designed, and so. But basically, in the directive, indoor climate is very well considered. It is said very strictly that energy performance cannot compromise indoor climate. And there is also indoor climate standard is one among these 40 EPBD standards, where all these input data related to indoor climate is defined, what is required in the energy calculations. So I would say that this is very relevant concern about the indoor climate, but now it has been taken into account very well in the directive, and also European standard is prepared for the indoor climate and for these input parameters required in the simulation. Indeed, nationally, you need to implement these indoor climate requirements in your regulation to be sure that they are followed. If this is only a standard, then when it is a guideline, can be followed, cannot be followed, and can cause problems in reality. But the question I will suspect more is related to these very complex technical systems that can be installed to these buildings, and engineers can propose these complex systems because the building needs to be nZEB building, and maybe they don't know that also simple and reliable systems exist. So that can be a real question. And if you have, as an engineer, you have very limited space for the technical systems, then you need to make very complicated systems, and this can be a real problem in practice. So it can be seen that the most severe problem will be in the operation phase and in the maintenance of these buildings.
Yes, but next question about this simple system. You show this cooling system using borehole system just in summertime. But have you experienced in long-term use of such systems, if you store, every year you store heat in those rocks? Perhaps next year you can't cool building because it's already, this heat is not moving.
So you are heating up rock. Yeah. So that was the reason the design temperatures of this system were flow temperature 15 and 20 return, because the ground temperature in the rock is, in Finland, it's about 7 degrees. So it's allowed to heat up, and then it will achieve some value. It's not more than 15. It's simulated for 50 years. It means, indeed, this is not the best system. The better system where you have a heat pump, you release and you will load also, use it both for heating and cooling, but in this case they want to use a district heating, and it's not maybe the best possible combination. It's more easy to apply a heat pump and then use only a little of this district heat for this peak load periods. Indeed, it's very good remark regarding this solution. I think it's not an optimal solution because you need to oversize these boreholes to be able to use these for next 50 years or something.
No, but we can overheat these ground waters anyway.
Okay.
Yeah.
Any more questions? Maybe some questions from as well students, not only professors.
Well, we will not stop before we have a question from students. But Andris. Yeah.
Energy consumption and so, especially for such objects with large staircases, exhibition halls and so on for public buildings. And what goes on with the industrial buildings and agricultural buildings, which are also with special shapes and different.
This has been one major debate, and actually this directive does not cover industrial buildings and agricultural buildings. But something else, and cubic meters can be quite relevant in industrial buildings. I agree. But regarding residential buildings and non-residential buildings, where indeed in European level this has been a major debate, what square meters we need to use. And end result has been to use useful floor area. So that's can be called net floor area or useful floor area. In some countries it is called heated floor area. In some countries it's conditioned floor area. But in any case it's useful. It's because you typically rent out some amount of square meters, and only the square meters are useful in residential or non-residential buildings. So that has been the logic. And indeed, I think the debate has been more between gross area and net area, not so much between cubic meters and square meters. So it's somehow accepted generally that in residential, non-residential buildings it should be measured in square meters, but the conclusion has been, and in the standards it's a useful floor area. Indeed, you need a national definition, and every country has many national definitions and many square meters defined in the different stages of a design. And that's a very common procedure all over Europe. You cannot compare these square meters directly between the countries. Everybody has slightly different rules. So it's a lot still to harmonize in these questions in Europe. Well, any other questions? Students? You all were sleeping?
Maybe some ideas in a way for future development.
Well,
thank you, Jarek, once again. I hope our relationships between universities become more stronger after your visit here. Thank you once again for your very developed presentation.
thank you for the invitation, and it has been very nice to see so many of students here in Latvia. And when I have attended the last conferences, I have also noticed that the Latvian delegation is quite impressive. And the major conference, REHVA, as it is a climate conference, so Climate 2013. Next year it will be in Prague in June. And it's also quite impressive how many papers have been submitted by Latvia. Actually, you have submitted more papers than Finland and Estonia, so it's congratulations. Keep this also in future, and it's really, I think it's very typical for all countries that we educate too less engineers, and regarding these nZEB buildings we need much more educated HVAC engineers and all other engineers capable for these energy studies. So it really will be a new field to be an energy expert in design projects for the construction companies or in the client side. We will need a lot of energy experts who will understand very well indoor climate issues, because if you compromise indoor climate, then you easily will lose all the budget related to energy, because these performance decrements, when we speak about human performance, these can be very remarkable, and indoor climate is indeed something that cannot be compromised. So it means you need to know very well these energy issues and also very well indoor climate issues to be successful in future, and to know everything related to technical systems. It's very important, and then to be somebody able to translate these technical issues to the clients and to the architects. So there will be a large challenge in the future. But I hope that we will start to construct such nZEB buildings, and it's just a learning process. Indeed, it will take another 10 years to learn these, and then it should be a common practice.